Hello everyone, and welcome to this little science talk. Tonight I'm going to tell you about nuclear fusion, but don't worry if you don't know what it is, or if you just want to know it a little bit better. This is not as complicated as it sounds. We are not going to dive into complicated equations or refer to concepts you don't know of. It is all going to be step by step and easy to follow along. Actually, this story is also made to help you fall asleep if you wish to. So don't hesitate to close your eyes and let yourself go whenever you feel like it. You can always come back later where you left. So tonight I will explain things like why the fusion of atom nuclei liberates energy, or sometimes not, sometimes it consumes energy. What the state of matter called plasma really is, how this fusion reaction could be voluntarily produced and contained inside a reactor to provide energy one day. What fusion reactors like Tokamaks and other designs could be like, and many other things. We have a lot to explore, so relax and let me do the work. As always, you will find timestamps in the comment pinned under this video, together with links to audio streaming sites like Spotify if you prefer to listen to my stories there. This one will be added soon. And also a link to my Patreon page if you wish to support this channel, keep it free of video ads, and download my videos and audios. But for now, let's begin our exploration. In another story, years ago, I told you about nuclear fission and how big atoms like uranium or plutonium could become unstable when they captured an additional particle, a neutron, which made them split into smaller atoms. This fission also liberated more free neutrons that escaped from the fissioned atom and could participate in other fission reactions, leading to a chain reaction. The fission of atoms liberates a lot of heat and a lot of very fast particles that are ejected from the fissioned nuclei. And this is the mechanism that produces energy in a nuclear reactor, in which this reaction is piloted to keep it working without snowballing. And the constant heat produced when the reactor is in operation is used to heat water that turns into steam and powers electricity generators, turbines. As a power source, nuclear fission has its advantages compared with fossil fuels or the various kinds of renewable energy sources. It is very compact relative to the power it can provide. A single reactor or a nuclear plant, which often has several reactors, can provide electricity to millions of homes. It also rejects no greenhouse gases, contrary to coal, oil or gas. and its production is fairly reliable over time. It can work day and night. It is not dependent on winds or the intensity of sunlight or the accumulation of water reserves behind a dam, like for hydropower. But its biggest flaw is the radioactive material it uses and the radioactive waste it produces. If there is an accident in a power plant working with gas, it can be bad, but it remains localized. Whereas a nuclear reactor with highly radioactive material in its core can be a big hazard if an accident happens and there is a breach of containment. And the problem doesn't end with the reactor. Once nuclear fuel has been used, it turns to waste, and these used nuclear materials have to be monitored for years, first in pools where they are kept underwater while they cool down, and then they have to be stored somewhere underground, because part of this nuclear waste will remain dangerously radioactive for hundreds of thousands of years. Nuclear plants and spent fuel tanks are operated with a lot of precaution. There are security measures, there are containment systems, but still, disastrous accidents have happened in the past. You obviously know about Chernobyl and more recently Fukushima in Japan. And even without accidents, the production of very long-life radioactive waste that future generations will have to deal with is a hazard and also a moral dilemma. So basically, nuclear energy with no radioactivity and no waste would be fantastic. It would eliminate all the main problems raised by nuclear plants since they appeared in the 20th century. And this is the promise of nuclear fusion, and the reason why it has been a topic of interest for decades. It could theoretically be a source of energy that uses no unstable elements for fuel, creates no dangerous waste, and on top of this is even more powerful than nuclear fission, which could make it very cheap. It sounds very good, and it is an exciting prospect for humanity, but it is not that easy. And I'm going to explain you why, how this power source works, how it could be harvested, and why it is technically so difficult. So to begin with, what is nuclear fusion exactly? It is a reaction in which two or more atom nuclei are combined to form one single nucleus. In other terms, it is atoms merging. As you know, atoms are made of different particles. In their nucleus, there are neutrons and protons, the difference between the two being that protons are electrically charged and neutrons are not. We'll come back to that. Around this nucleus, there are one or several electrons, which have an opposite electric charge to protons. And typically, an atom has the same number of protons and electrons, which makes it electrically neutral unless electrons are missing. Even though atoms are made of smaller particles, they are considered a relevant unit of matter for mainly two reasons. First, because they define each element depending on how and how many of these particles combine protons, neutrons, and electrons, you get different elements with different properties. Atoms of hydrogen, iron, copper, gold, or carbon, they are all made of the same basic bricks, but it is how many and how they are combined that give them different properties. This makes the atomic level very relevant to physics, chemistry, to more generally the understanding of the properties of matter. The second reason that makes atoms relevant is that most of the time atoms around us on our planet or other planets of the solar system are very stable. They keep the same structure over very long periods of time because it takes extreme conditions to break or change the nucleus of an atom. With very little risk of error, I can safely tell you that almost all the atoms in your body have existed for billions of years. Maybe not combined together in the same molecules, but as atoms they already existed in the early stages of the formation of the solar system. Outside of stars like the Sun, and we're going to talk about that extensively in a minute, atoms generally don't change. The only exception on our planet would be a few big atoms that are naturally unstable and experience decay. They fission naturally because their nuclei formed with a number of neutrons that makes them prone to breaking apart. But this is a very small share of matter on Earth. Other than that, atoms exist for very, very long periods of time. But this raises a question. Why are there atoms? Why do the particles, the components of atoms, stick together and so firmly instead of flying past each other? It is important to understand it to grasp what happens in a fusion reaction. There are basically two forces that keep atoms together. The first one has to do with electric charge. I told you earlier that protons in the nucleus had a small electric charge marked as positive, and electrons have a negative charge. This is what bounds the nucleus and its electrons. Opposite charges attract each other, and similar electric charges have the opposite effect, they repel. As a result of this, a nucleus which is positively charged will attract electrons that will swarm around it. This is the first force that keeps atoms together, the one that binds electrons to a nucleus. But this raises a common sense question. If electrons are attracted by the nucleus, why don't they just merge with it, collapse into it? We may ask this question because of how atoms are generally represented since the 19th century. The typical picture of an atom is like a mini solar system with electrons orbiting around a nucleus, like planets orbit around a star, but on a very, very small scale. So, based on this representation that still dominated physics a century ago, the first hypothesis was that electrons kept separate from the nucleus because of centrifugal force. If they revolved very fast around the nucleus, then it made sense that they wouldn't fall into it, because this centrifugal force would maintain a distance. In that hypothesis, the orbit of the electron around the nucleus would have been the product of an equilibrium between the electric attraction, the force that pulls the electrons towards the nucleus, and the centrifugal force that pushed it away. This could work, but only if we accept the representation of an atom as a tiny star system. But what modern physics tells us is that this representation is not accurate. It appeared about a century ago, in the 1920s, that a tiny object such as an electron could not be treated as a classical particle with a definite position and a definite velocity. This is the realm of quantum physics on this scale, and we cannot always know where an electron is. We can only observe its manifestation sometimes, and it doesn't follow an orbit around the nucleus. It manifests itself near or even sometimes inside the nucleus. This is not our topic tonight, but just bear in mind that the traditional image of the electrons orbiting around the nucleus is something that modern physics no longer validates. It is still useful to picture an atom, understand its interactions, but a better image of what an atom is would be with a nucleus and a kind of cloud around it. A cloud that represents all the locations where electrons are likely to be at any given time if we observe them. This is hard to picture mentally, and this is probably why the old atom picture with electrons in orbit is still enduring. But that was just a tangent to explain why the idea of electrons falling into the nucleus because of electric charge's attraction doesn't really have a basis. It is more a false problem created by our traditional representation of atoms. And for the topic we discussed today, let's just bear in mind that the first force that holds atoms together is electric charge that binds electrons to the protons contained into the nucleus. But at this point, you could tell me that we have a problem. If opposite electric charges attract and similar charges repel, then the nucleus should not exist, it should explode, because it contains protons that have the same positive charge. Why do these particles with a similar charge stick together? Obviously because there is a second force at play, one that is stronger at this scale and more than compensates for the electric force. All the more that the closer charged particles are, the stronger the electric repulsion is. This is why this force that keeps protons and neutrons together in the nucleus has been called the strong force or strong nuclear interaction. It has been identified in the 1970s, it is not that long ago, as one of the fundamental forces of physics. What is a fundamental force or a fundamental interaction? They are existing forces that do not appear to be reducible to more basic interactions. We can observe them, measure them, anticipate their effects, but they cannot, in the current state of science, be explained by another interaction behind it. 4 of these fundamental forces have been identified until now, and we just talked about 2 of them. We talked about electromagnetism which is at play in the attraction between protons and electrons that keeps electrons bound to atoms. We know this force is there. We can explain and measure how it works, but we cannot go much further and understand why, at least until now. It is the same for the second force we just talked about, the strong nuclear interaction that holds nuclei together. It also holds individual particles like protons and neutrons together, because they are made of even smaller particles. And we know a bit about the how. This force is carried by subatomic particles called gluons and mesons, but the question of the why, or if there is another interaction behind it, remains unanswered. The strong nuclear force works on a very small scale, a very small range, the scale of a nuclei or individual particles. But at this range, it is very, very powerful. At a range of about the radius of a proton or a neutron, it is more than 100 times stronger than electromagnetism, which is why it easily compensates for the mutual repulsion of protons due to their similar electric charges, and it holds the nucleus together firmly. There are two more fundamental interactions. Another that exists at a subatomic scale too has been called the weak nuclear force, or weak interaction. Its range is even shorter than the strong interaction. It acts inside particles, and it is the hardest to understand. We don't need to go too far in that direction tonight. But let's keep in mind that the weak force is an interaction that exists inside the components of atoms. It doesn't bind them together, but plays a role in their transformation. For example, a proton can become a neutron. It can lose its electric charge. The weak force is important in processes of decay inside atoms, which come with the emission of radiations. So it is a third force, and the fourth fundamental force, which manifests itself on a much larger scale, is gravitation. This is probably the one we are most familiar with. It does not only keep together star systems or planets, it is also what gives us weight, makes objects fall. Here again, theories have explored gravitation. They have helped measure and define it better. For example, Einstein's theory of relativity, which defined gravitation. I made a story about it long ago if you want to know more about this theory and its implications. But even though the theory of relativity shed a new light on gravitation, it explains the how it works, but it does not offer another more basic interaction that would be behind it. This is why gravitation is considered a fundamental force too. Now this list of four, electromagnetism, strong interaction, weak interaction and gravitation, is not necessarily closed. Maybe a fifth one will be added to the list one day. Some physicists think there could be yet another one. Or the list could shrink. Maybe two or more of these fundamental forces could be the product of the same basic interaction that has not been understood yet. One of the goals of physics, the discipline, that is still out of reach today, is to try to unify them, to understand why they exist, possibly as different manifestations of a yet to discover interaction. it will certainly never solve the ultimate why. If we discover another more basic interaction behind them, we still won't have an explanation of the why this other force exists. This is the field of metaphysics, what is above or beyond physics. But it would be fascinating and possibly have applications to unify some or all of these fundamental forces in a theory one day, if this is possible. So, now that we have seen a little bit more of why atoms held together and what they were made of, let's return to fusion and try to answer this question. Why would the fusion of two nuclei liberate or consume energy? Because, after all, why combining two things together would release anything? We have seen that nucleus, that is to say protons and neutrons, were held together by the strong nuclear force. This is key to understand what happens when nuclei merge. We know it since Einstein's theories. In physics, matter, a mass, a quantity, and energy, that is to say, the property that must be transferred, applied to a body to perform work on it or to heat it, are not entirely separate things. They are manifestations of the same thing. It defies our conventional imagination and our sensible experience. But matter and energy are the same thing, hence the famous equation E energy is equal to m mass multiplied by the square of light speed. E equals mc squared. For more explanations about this, you can also listen to the story about the theory of relativity. But for tonight, let's just keep in mind that if the mass increases, then energy has been consumed, absorbed, and if a mass decreases, then energy has been liberated. What does it tell us about atom nuclei? That theoretically, if you take several particles that are independent, and then they form an atom nucleus that is bound by the strong nuclear force, then a form of energy that wasn't there before, when the particles were separated, has appeared, and it now binds them. The particles were not bound, and now they are. This work of binding them together is energy. But energy does not appear out of nowhere. So where was it before? It was in the mass, in the matter. And this leads to the following observation that sounds counterintuitive, but it has been verified long ago. When you put particles together to form a nucleus, the mass of this nucleus is less than the sum of the masses of the particles, because a little bit of their mass has been changed to energy. This energy is called nuclear binding energy, and it is one of the applications of the E equals mc squared equation. If you know the measure of this energy, you can use the equation to calculate how much mass has disappeared, and vice versa. Knowing how much mass has disappeared, you can calculate the energy liberated. It also means that to disassemble a nucleus into separate protons and neutrons, one needs to apply to it at least as much energy as the nuclear binding energy, the one that keeps it together. The loss of mass when the nucleus formed represents the energy that was released at the time of the formation. This connection, this equivalence between mass and energy, is the reason why energy may be released, or sometimes consumed, we'll see that later, when atom nuclei change size and composition. This is why fission in a nuclear reactor releases energy. When a heavy nucleus fissions into two lighter ones, less binding energy is required, and so the difference is liberated as heat and radiations. More specifically, in the case of a fission reaction, this excess energy is emitted as gamma rays, an electromagnetic radiation, and also as kinetic energy, that is to say, the movement, the velocity of particles that are ejected from the nucleus. In fusion, when nuclei merge instead of fissioning, there is also a variation of the quantity of binding energy required. If it is less, then the difference is liberated, released, or sometimes it can be more. Fusion may also require more binding energy for the new nucleus to hold together, in which case the fusion reaction has a negative energy balance. One has to give energy to the particles, and in that case, the reaction is called endothermic, whereas when it liberates energy, it is called exothermic. Now, if we want to harvest energy from nuclear fusion, we need to combine nuclei that will need less energy when put together into a heavier nucleus, a heavier element. But what makes the difference between fusion reactions that liberate energy and the ones that consume some? The size and the structure of the nuclei are key. Typically, the fusion of light, small nuclei, elements that are the first ones in the periodic table of elements, like hydrogen or helium, liberates a lot of free energy. The most common type of fusion reaction in a star, like the Sun, is the fusion of hydrogen nuclei. The most abundant type of hydrogen atoms in the universe, more than 99% of hydrogen, only has one proton and no neutron. So basically, an isolated proton is a hydrogen nucleus. When hydrogen atoms only have one proton as a nucleus, they are called protium. But as you know, there are variants of atoms. Sometimes they can have additional neutrons in their nucleus. These variants are called isotopes. And hydrogen has one which is less common than protium, but still fairly abundant in the universe, called deuterium. Its nucleus contains one proton and one neutron. There is another isotope called tritium, which is one proton and two neutrons as a nucleus. So, when you put together two such nuclei, let's take, for example, two isolated protons, the most simple kind of nuclei, you get a more massive nucleus, but as we have seen, not as massive as the sum of the two protons, because a part of their mass has turned to energy. In practice, inside a star where this reaction takes place, neutrons are added to the mix. It is not just two protons, and the fusion of two hydrogen nuclei can give a variety of isotopes of helium, the element just after hydrogen in the table of elements. because it has two protons in its nucleus. Helium with two protons and zero neutron is very unstable and will quickly break apart. But helium-3 or helium-4, that is to say with 3 or 4 particles in the nucleus, 2 protons plus 1 or 2 neutrons, these are very stable. The constant fusion reactions that happen in a star are what powers it, because they liberate enormous amounts of energy, radiations, heat, particles with kinetic energy. During most of its lifetime, a star lives on the fusion of light atoms, essentially hydrogen, and then helium to a lesser extent, and it creates heavier nuclei, but not the heaviest elements, because, as we just said before, these ones require an absorption of energy. Their creation costs energy instead of releasing some. The limit in the list of elements where fusion begins to need an input of energy is an isotope of iron called iron 56. It has 56 particles, protons and neutrons, in its nucleus. The creation of elements that are heavier than that via a fusion reaction is endothermic. It consumes energy instead of releasing some. And for that reason, it is believed that the appearance of these heavier elements takes place in the last phases of a star's life, when it has exhausted a large part of its hydrogen available and ends in an explosion, a supernova, followed by a collapse. The energy released in a fraction of a second at that moment is so gigantic that heavy nuclei fusion, absorbing some of this energy. But what is important to understand here is that to harvest energy from a fusion reaction, you need to make protons come close enough from each other that the strong nuclear force, that is very powerful but has a very short range, can come into play and overcome the repulsion between the protons that is due to their electric charges. Before they are close enough, they repel each other, and this natural repulsion needs to be overcome by giving them enough energy so they can beat the electromagnetic force. In other words, to harvest energy from fusion, you need to spend energy first. And then, when fusion happens, you will get back more than what you spent. But there cannot be fusion without an already intensely energetic environment. This is why it happens in stars, where heat and pressure conditions are extreme due to gravitational forces. The star is a very large and massive body. The forces inside defy imagination. But in space, in the void, on planets, fusion cannot naturally occur. This is a big difference with fission energy. Fission happens because of the natural instability of nuclei. It occurs naturally on Earth, which is why there is a low-level natural radioactivity around us all the time. In a nuclear reactor, we just put a lot of fission-prone, of fissile material together, and then we start and pilot a reaction. But we don't need to give it energy for the fission reaction to begin. Fusion is much harder to ignite. It is theoretically conceivable to make it self-sustained once fusion reactions begin inside a closed, contained space, they can liberate energy that will allow more reactions to happen. But the ignition costs energy. A challenge to turn fusion into a power source is to create an environment inside a reactor where fusion happens continuously, and the energy it liberates allows more fusion reactions to take place, so that the balance of energy is positive. And this is the technical challenge we are now going to discuss. How to create a confined reactor inside which temperatures are somewhat similar to the inside of a star. In reality, even higher, because inside of a star there is a very high pressure due to gravitation that cannot exist inside a reactor. So the temperature needs to be pushed even higher. We are talking more than 100 million degrees. That is to say, a temperature that can quickly melt any material we know of. But this incredibly high heat needs to be confined inside the reactor, and on top of that, we need ways of extracting the energy liberated by fusion. This is the extraordinarily complex engineering challenge raised by fusion power. Inside a star, a long-lasting fusion reaction can exist because gravitation provides confinement. The star is held together by gravitation. It is very large, so reactions can take place inside, and yet the star does not explode or dissipate in space because gravitation pulls all its components towards the center. For artificial fusion to be viable, we would need to recreate these conditions. But obviously gravitation cannot provide confinement because it would be on a much smaller scale. In a nuclear reactor, this problem does not exist because there is no requirement of high temperatures and pressure for fission to happen. So a tank filled with water and rods of fissile material, of fuel, is sufficient, and provided the heat from the reaction is evacuated constantly, this is how we harvest calorific energy in such a reactor. The tank will not melt because the temperature of the water inside does not go above a few hundred degrees. The temperature necessary inside a fusion reactor is completely on another scale. Punctually, where the fusion reactions take place, it is more than 100 million degrees. And even if this doesn't touch the walls of the reactor, these walls would have to bear extremely high temperatures. The constraints are challenging, to say the least. And this is why, from the moment artificial fusion as a source of power began to be researched in the 1950s, the idea of confining the reaction inside a magnetic field appeared. But what does it mean exactly? First, we need to talk about what needs to be confined. What happens to matter when it is exposed to extremely high temperature? Matter in such an environment turns into plasma. But what is plasma? Generally, we learn in school that matter has three fundamental states: solid, liquid, or gas. The understanding of this in the 18th and 19th centuries was an advance in modern physics and chemistry, and these categories remain useful because indeed this is how we encounter matter on Earth in our daily lives. Assuming we are at sea level pressure on Earth, if you take a solid and heat it, it will turn to liquid, and if you heat it more, it will become gas, But these three states do not really grasp the entire spectrum of states of matter. For example, recently I told you about supercritical fluids in a story about astronomy. The atmosphere near the surface of Venus, or the layers inside gas giants like Jupiter, would be in that state that is neither liquid nor gas. There is another state called plasma, and even though we naturally encounter it rarely on Earth, it is actually by far the most abundant state of matter in the solar system, and also probably in the universe, because this is the state of most of the matter inside the stars. And the Sun, just to take our system as an example, accounts for more than 99% of all matter in the solar system. Plasma is what you get when you superheat a gas, so hot that the electrons are ripped away from the atoms, forming what is called an ionized gas. Ionized because ions are particles, atoms, with a positive electric charge. A proton alone, or an atom that misses an electron, are ions. Taken as a whole, a plasma does not necessarily have a positive or negative electric charge, because the charges of its particles compensate each other, as long as it contains as many electrons as ions. But the plasma acquires different properties, and the most important is that it becomes electrically conductive. It reacts to magnetic fields, because this cloud, this soup of particles, will move collectively due to its electric conductivity. Now, the concept of plasma in everyday language is a bit blurred, because there is no exact definition of the transition point between gas and plasma. There are things like neon lighting or plasma screens. These have more or less disappeared now. They have been replaced with other technologies like LCDs. But these are applications that use plasma, and obviously a neon bulb or a plasma television did not warm up to thousands of degrees. This is because they contain gas that is only partially ionized. It is not pure plasma, but it still has specific properties that can be used when you power them with electricity. Ionization is a spectrum. It can be only a few particles or all of them. The plasma we are talking about in a star or inside a fusion reactor is fully ionized. It is so energetic that atoms have been stripped of all their electrons, leaving only bare nuclei. This is what is needed for fusion inside a plasma to happen. A soup or a hot cloud of nuclei and free electrons, inside which nuclei that are now positively charged electrically are energetic enough, very hot, very fast, that they can collide despite their electric repulsion. They have the same electric charge, you remember. They can come close enough for the strong nuclear force to overcome their electromagnetic repulsion, and they can fusion into heavier nuclei. The elements, the fuel that can be used, are very important here, because as we have seen before, only fusion of small nuclei releases energy. They are called exothermic, as opposed to endothermic when they consume some. So the best fuel possible is hydrogen, because first it is the lightest possible nucleus, and second it only has one electron, so it is easier, it requires less temperature, less energy to ionize it, to rip the single electron off from each atom and turn it into an ion. The confinement of a plasma that is heated at more than 100 million degrees is inconceivable with walls. They would melt immediately. But as we have seen before, plasmas are electrically conductive, and so they can be controlled with magnetic fields. Possible designs of fusion reactors take advantage of this to confine the particles as they are heated. The plasma cannot touch the walls of the reactor, but what if we control the plasma inside, in suspension, with magnetic fields, so that it doesn't touch the walls? This idea, which is also a necessity, is the basis for all the designs of fusion reactors, including the most famous of them called the Tokamak. Tokamak is an acronym in Russian, and it has passed to other languages, but the name comes from Russian because this type of device was conceptualized in the 1950s by Soviet physicists. For the record, one of them was Andrei Sakharov, who later became very famous for being a dissident to the Soviet regime and a human rights activist. So the tokamak is only one of several types of magnetic confinement devices that were and continue to be developed to produce fusion power. If one day we manage to have a functioning fusion reactor, that is to say with a positive energy output, it will not necessarily be a tokamak, but it is one of the best, if not the best candidate. The inside of a tokamak looks like a ring, and it is made to contain plasma in the shape of a torus, which is the complicated word to say in the shape of a donut, a thick disk with a hole in the middle. Why a donut? Because it is an optimal shape. Having magnetic lines that wind around the torus strongly helps to stabilize, to keep in place the plasma. Other types of designs have been imagined before or after. They are called stellarator, Z-pinch or magnetic mirror. We won't go further tonight into these types of devices. There are different approaches to plasma confinement with magnetic fields. They all have or had, when they were abandoned, their advantages and disadvantages. The biggest disadvantage for such a system is the loss of plasma. If it doesn't stay in suspension but leaks, escapes from the zone where it should be confined. You understand the complexity of this. It is necessary to make plasma that will be several million degrees hot stay in suspension, levitating, inside a reactor, while at the same time particles inside the plasma move at speeds that defy imagination. When it was invented in the 1950s, the tokamak design was a leap forward, because it suppressed the instabilities that plagued earlier designs. At the end of the 1960s, tokamaks looked very, very promising. They had not achieved a net positive output of energy, but they had better results than any other designs, and that's why they multiplied around the world in research facilities. But then bigger and bigger devices made with the hope of reaching a positive output disappointed. They encountered new problems when they were built on a larger scale, and there were disappointments in the 1980s. the reason why the output remains negative is not that these reactors don't achieve fusion, they do. They heat plasma in suspension. This is complicated technically, but doable by inducing a powerful electric current inside the plasma. You remember the plasma is conductive. Then fusion reactions begin, and new fuel, new hydrogen has to be introduced to keep the reactions happening. But the problem is that the heat generated by the reactions is not sufficient to make more reactions happen and make the reactor self-sustainable, while at the same time harvesting some energy from it. The plasma cools down when heavier elements, the products of fusion, accumulate in it. The plasma is not stable enough, it leaks, so more power has to be given to the reactor to make it continue to work. And instead of producing a net surplus of energy, the reactor needs an input. As of today, the machine that holds the record for fusion output is the JET, J-E-T, the Joint European Torus, which is located in England. Its output reached 16 megawatts, but for an input of 24 megawatts, so it is still significantly negative. But still, progress has been made in the past decades. These performances are well above the ones that were achieved with the very first devices, and hopefully they will keep improving with better materials, better fuel, bigger devices too. Research continues around the world, and because it requires extremely complex engineering, expensive equipment, large teams of scientists and technicians, some of these efforts are international. The primary international effort to advance towards a practical fusion reactor today, and it is based on a perfected tokamak design, is ITER, I-T-E-R, the International Thermonuclear Experimental Reactor, a project that is still under construction in southern France, and when it opens in a few years, it should be the largest tokamak in the world, and more generally the largest experiment for containment of plasma, with 10 times the volume of any other tokamak operating today. Parts of the hopes placed in this project rely on the change of scale to be able to generate a net positive output. If this works, how could such a reactor harvest energy? The energy liberated by exothermic fusion comes under the form of heat and particles that have kinetic energy. They are expelled from the new nucleus, and when these particles are neutrons, they are not bound by the magnetic fields that keep the plasma in place. They have no electric charge, so they are not affected by a magnetic field. So they are going to escape the plasma and hit the walls of the reactor, which will heat them up. Through this mechanism, calorific energy, heat, can be extracted. Like in a fission reactor, it can be extracted by a fluid, water, in circulation that comes in contact with the hot walls and be used as steam to power turbines that produce electricity. If this can be achieved, the reactor would have several advantages over other energy sources. There would be no release of pollutants, like with fossil fuels, and the main products of hydrogen fusion are helium atoms, which are not radioactive nor dangerous. there would be only a marginal creation of radioactive waste, still a little bit, not because of the fusion reaction itself, but because of the absorption of neutrons by the surrounding material inside the reactor. But not a big deal as far as we know today, because these byproducts would have a short half-life. They would quickly lose their radioactivity, and they are way less toxic and dangerous than the waste products of a nuclear reactor. It is almost sure that we will not see a functional fusion reactor this decade, and probably not in the next neither. So there is very little hope that they can solve energy issues in the short term. But however complex the engineering and difficult the task, the potential rewards justify the effort to design one. The fuel would be cheap, hydrogen is abundant. The one that should be used in such a reactor would have to be processed, because it would work with hydrogen that has one neutron. We talked about it before, the one called deuterium, and tritium, the one with two neutrons. Both, especially tritium, don't occur much naturally, so they would have to be produced, but that would still be cheap. The cost of electricity produced by fusion would essentially be the amortization of the reactors. They would be very costly at first, and the cost of maintaining and operating them. But just the environmental promise of very low waste and no greenhouse gases is attractive. We have reached the end of our little journey for tonight. I will put more science stories in the description, like the journey to the infinitely small, or the one about cosmology. Or you can just close your eyes for now, let go, and fall asleep. Sleep well. Sweet dreams. Au revoir.